All right, so this is part B to problem 10 for the behavioral analysis problems. I did part A in the previous video where I showed a monotone, or we proved that a sequence was monotone and bounded, which implied that it converges by the monotone convergence theorem. And then we found the value for the limit using the Inf Tail Theorem. And so we're going to do the same process for this problem, which comes from Cummings' textbook. And this is exercise 3.24, and it's a recursive sequence. So the sequence is defined by a1 being the square root of 2, and the a sub n plus 1 is equal to the square root of 2 plus a sub n, where n's a natural number. So we're going to show the sequence converges, and then actually it tells us to show the limit itself is 2. So the previous one actually found the limit. I'm going to do the same process for this, and you'll determine that we get 2 for the value. All right, so like last time, I'm going to use the monotone convergence theorem. So apply. All right, so that was my dog that was barking in the background, so excuse that. But anyways, what I'm going to do is apply the monotone convergence theorem, so MCT. And so I need to first show that our sequence is bounded, or show that it's monotone. I'm actually going to do the monotone first. I'll show that our sequence is monotone. And then show that it's bounded. And so once I've shown these two things, then that's going to imply that the sequence converges. All right, so that's the first part of the proof. Now, when I'm going to determine that its limit is 2, to find the limit itself, so by the Inf Tail Theorem that I used in the previous video, the limit of some sequence an is equal to the limit where you have the subsequence where you do the and it's going to be of the nth tail of that sequence, and so it can equal a sub n plus 1. So they're going to be equal to each other by that nth tail theorem. All right, so that's how I'm going to structure the problem. All right, and again, I pretty much summarized the problem from the textbook from Cummings. He actually tells you to do like part A, part B, and part C to the problem. Although what I do in this is pretty much showing all those parts, maybe a little bit more to it than what those parts ask. So I'm going to first show it's monotone. So claim our sequence is monotone. And I'm going to say it's going to be monotone increasing. In other words, our sequence is such that we have A1 less than or equal to A2, less than or equal to ... less than or equal to AN, less than or equal to AN plus 1, and so forth. All right, so that's what we're going to show. And first, let me write down the sequence again. So recursively, you have A1 is equal to the square root of 2, and then the n plus 1 term is defined to be the square root of 2 plus AN. All right, so we're going to do induction proof. That's supposed to be a PF for proof. So first the base case. So our first value, A1, is equal to 2. All right, then we have that if, so we know, so A1 is equal to the square root of 2. So if we add 2, then 2 plus square root of 2 is greater than the square root of 2. And hold on a second, let me restructure this. 2 plus square root of 2 is greater than 2. And we know that our sequence is defined so that the n plus 1 term is equal to the square root of 2 plus an. Well, the first term is square root of 2. And so what this is saying is that this is essentially a2 squared, and then 2 is a1 squared. So we have a2 squared greater than a1 squared. And we know by property of real numbers, that's if and only if a2 is greater than a1. All right, so hopefully that makes sense. As we have a2 is equal to the square root of 2 plus a1. Well, a1 is the square root of 2. So it'll be 2 plus the square root of 2. And so a2 squared, just get rid of the square root, and then that gives you 2 plus square root of 2. And so that's what this is. That's a2 squared. And a1 is square root of 2, so a1 squared is 2. So I've shown that a2 squared is greater than a1 squared, and that's if and only if a2 is greater than a1 by property of real numbers. So the base case is taken care of. So now the inductive part, the inductive part, that's what I like to call it. Assume for some k, we have that ak squared is greater than, ak plus 1 squared is greater than ak squared. And that's, again, that's if and only if ak plus 1 is greater than ak. All right, so then using our inductive hypothesis, so that ak plus 1 is greater than ak. Now, if we add 2 to both sides, then this will be 2 plus ak plus 1 is greater than 2 plus ak. Now, what is 2 plus ak plus 1? Well, we know that the sequence is defined so that the n plus 1 term is the square root of 2 plus the nth term. So if we square both sides, that means the n plus 1 term squared is equal to 2 plus the nth term. So we get rid of the square root. So this really is, by how our sequence is defined and squaring it, this is really ak plus 2 squared. And then this is greater than, and this is 2 plus ak, that's our ak plus 1 squared. All right, and then if that's true, then again, we can do an if and only if. That means ak plus 2 is greater than ak plus 1. All right, so now we've shown for all n, so this is our inductive hypothesis was using ak plus 1 squared greater than ak squared. If and only if ak plus 1 is greater than ak, then we use that assumption, add 2 to both sides, and then we used our definition since an plus 1 is the square root of 2 plus an, then an plus 1 squared is just getting rid of the square root. So you just have 2 plus an. All right, and that's how I proved it, just because I didn't like dealing with a bunch of square roots. All right, so since the next term is greater than the previous term, then we have it as an increasing sequence. So we're all in. An plus 1 is greater than or equal to an. Or in other words, an previous term is less than or equal to the next term. So we've shown that our sequence is increasing. All right, now the next thing I'm going to do is, so that was the claim for monotone increasing. Now I'm going to claim that it's bounded. So sequence an is bounded. First, I'll say that it's bounded below by 0. As long as I've bounded lower bound and then upper bound, it does not necessarily need to be the inf for the soup. As long as I find a bound, that works. So consider 0 as a lower bound. Well, 0 is less than our first value of the sequence, which is a1, and a1 is square root of 2. So 0 is less than square root of 2, which is our first value, a1. Our sequence is increasing since we determined that our sequence was increasing. It follows that zero is going to be less than or equal to all the terms. We have 0 is less than or equal to a1, less than or equal to a2, dot, 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 and it keeps going like that. So 0 is a lower bound. All right, so that part's the easy part. Now we'll do the upper bound. Now I'm going to say consider 2 as an upper bound and show that it is an upper bound. And to do this, proving that it is an upper bound, I'll do an inductive proof. So what does it mean to be an upper bound, first off? So we wish to show that for all our terms an, they're going to be less than or equal to 2 for all n. All right, that's what we're trying to show for 2 to be an upper bound. So the base case our first value, a1, is the square root of 2, which is certainly less than 2. Now, this is true if and only if I add 2 to both sides, we have the square root of 2 plus 2 is less than 2 plus 2. And that's if and only if you square root both sides. So this will be square root of 2 plus 2, which I could write it as the square root of 2 then plus the square root of 2. And that's less than the square root of 2 plus 2, which is square root of 4, which we know is 2. And what is this? This is a2. So a2 is defined to be the square root of 2 plus a1, where a1 is square root of 2. So we have a2 is less than 2. All right, so I did a little bit more than just a1. I showed that also a2 is less than 2. So now assume for some k, we have that ak is less than or equal to 2. And I'll do kind of what I showed here. I'm going to add 2 to both sides. So I have 2 plus ak less than or equal to 2 plus 2. And then I can square root both sides. So that's less than or equal to the square root of 4, which is 2. Well, the square root of 2 plus ak, that is ak plus 1. So we have ak plus 1 is less than or equal to 2. So these are if and only ifs. Using our inductive hypothesis of ak being less than or equal to 2, we've deduced that the k plus 1 term is also less than or equal to 2. So 2 is an upper bound from this inductive proof. Hence, we have an is less than or equal to 2 for all n, meaning 2 is an upper bound. So now we've shown that we have 0 as a lower bound, we have 2 as an upper bound, so our sequence is bounded. So we've shown for all terms, 0 is less than or equal to an, which is less than or equal to 2 for all indices n. That just means our sequence is bounded. All right, since now we've shown that it's increasing and bounded, so the sequence converges by the monotone convergence theorem. All right, now I'm going to use the nth term theorem to find its limit. So to find its limit, suppose we know it converges, so let's say the limit converges with some value a. Then we can say by the nth term, or Inf Tail Theorem, we have that the one tail which is the sequence a sub n plus 1, also converges to the same value a. So we have the limit of an, which is equal to a, which is also equal to the limit of a sub n plus 1. And what was a sub, how our sequence was defined? The n plus 1 term was the square root of 2 plus the nth term. So we could say a is equal to the limit, and then our sequence is defined as the square root of 2 plus an. You can square both sides, so you get a squared. So and we know the limit of an is a, and then so we get a squared, and that gets rid of the square root by squaring both sides is 2 plus a, because we know the limit of an is a. Then I can bring the terms over to the right side, or sorry, the left side, and I'll have a squared minus a minus 2 equal to 0, and then I can factor this into a minus 2 times a plus 1. And my two factors are going to give me the solutions a is 2 and negative 1. But we discard the case of negative 1 since our sequence is bounded between 0 and 2. So a is 2 is the correct limit. All right, and that was an example that I wanted to do. This is part B to problem 10. And so I essentially, it was a recursive sequence, and I showed it was in monotone and bounded. And then I calculated its limit using this Inf term theorem. And so specifically, I used the one tail, or sorry, not Inf term, Inf Tail Theorem. And so using the one tail, which is just using 1, so normally the nth tail is defined to be a sub n plus m, but I just use m being 1. All right, and that's how I calculated its limit and got it to be 2. So that's it for this problem.